Our next speaker is Daniele Colosi. He's from Universidad Nacional Autónoma de Mexico, and he will be speaking about the detection of evanescent particles. So I will give you a warning before 2 minutes till the end, and the floor is yours.
Thank you very much. Thank you to all the organizers of this nice conference. So I will present very preliminary results obtained in collaboration with Robert Oeckel and Adamantia Zampelli. Let me also advertise that Robert will give a talk on Friday. So to explain the title of the talk, I will divide my presentation into pieces. So the first one is a very brief presentation of a new formulation of quantum theory called the general boundary formulation. Then I will introduce a specific region, space-time region, which is called the hypercylinder region, and then introduce a new scheme of quantization adapted to the evanescent modes of the field that appear in this region. And this will solve the problem of defining what is an evanescent particle. Then for the detection of this particle, we use an Unruh-DeWitt detector, which is, well, many of you are very familiar with this. And then I will conclude very briefly. So why do we need a new formulation of quantum theory? Because there are serious limitations with the standard one, okay? So in particular, we want to have a local, space-time local description of physics, something that is not yet achieved. And also we will want to solve some of the problem that are present in the standard formulation related, for example, to perturbative techniques or GS metrics, or for example, how to define a vacuum state in a general curve space-time if we don't have any isometries to select one specific vacuum. How do we quantize evanescent modes? And of course, the big problem of formulating quantum theory of the gravitational field. Now, it turns out that there is a new formulation that solves almost of this problem, almost, apart from the last one. And it's called the general boundary formulation. So let me give you just the idea of this formulation. So this is based on the mathematical framework of topological quantum field theory. So it's based on an assignment between algebraic structure and geometric one. So in particular, we will consider as a geometric structure an hypersurfaces, which is an oriented manifold of dimension d-1 if d is the dimension of the theory. And at the classical level, we associate a space of germs of solution in the neighborhood of these hypersurfaces. At the quantum level, this will be promoted to an Hilbert space of state. The second type of region of geometric object is a region, a space-time region, with its boundary, dm, and then here we can define a space of solution while defining inside the region. And at the quantum level, we can define an amplitude map, which is a map from the Hilbert space associated to the boundary to the complex number. And this really is the generalization of the standard transition amplitude, okay? If we have observable, we can simply modify this map and obtain what we call the observable map. Now we have a set of axioms in the very spirit of topological quantum field theory that essentially guarantees the consistencies of these assignments and the operation that can be done with this structure. We also have a probability interpretation from which we can extract really physical information from this, which again is a generalization of the standard probability rule, the Bohr's rule, okay? Now the key point here is that we don't make any specific choice of the region or its boundary. So let me present you a very special region, which is the hypercylinder region. So this is a region in space-time, let's say Minkowski, and the boundary is a tree-ball in space at fixed radius extended over all of time. So the boundary is time-like and connected, okay? So if we have state on the hypercylinder, so we will not have initial initial and future state or in and out state, they're just connected. So the solution, the classical solution parameterized in terms of this, on this function that you can see here. So we use spherical coordinates, so we have spherical harmonics, and we have spherical Bessel function, this f, that depends on the value of the momentum, which essentially is determined by the energy of the particle or the state, and here we have the mass of the field. So if the energy is larger than the mass, so we have what we call the propagating solution, determined by this Bessel function. These are angled functions, spherical angled function. And if the energy is smaller than the mass, we have a evanescent solution, okay? So the space of solution really decomposes into two pieces, the propagating one and the evanescent one. Now we want to go to the quantum theory. So we complexify the space of solution, we define an inner product, which is defined in terms of the symplectic structure and the complex conjugation. We introduce a set of modes which are orthonormal with respect to this inner product. We identify the positive definite subspace and the negative definite subspace with respect to this inner product. So we have a polarization of our space of solution. And then we can, for example, apply a canonical quantization prescription to obtain the quantum theory. And we have the vacuum, which is annihilated by all the annihilation operator associated with this subspace. And then the relation within the vacuum space, the vacuum state, and the positive definite Lagrangian subspace is very, it's a one-to-one relation, actually, because it turns out that this polarized space, the L plus and the L minus, are really Lagrangian subspace in the sense that satisfy certain property, which is written here, the isotropy and coisotropy properties. And there is a one-to-one relation, as I said, between positive definite Lagrangian subspace and vacuum state. And if you want to see the detail of this, so I refer to this paper. So going back to the hypercylinder region, as I said, we have two kinds of solution: the propagating solution, which are simply oscillating as the standard plane waves in Minkowski, okay? And we also have evanescent solution, which are either exponentially decreasing function in the radius, like the KL solution, or the other one, the K tilde, which are exponentially increasing solution, okay? So a general solution of the equation of motion, of the classical equation of motion, as a propagating piece, which is this one, okay? So we integrated with a value of the energy which is larger than the mass, and an evanescent piece, which is this one, okay? So let's go to the quantum theory. So for the propagating sector, we have our inner product. We identify very easily which is the positive definite Lagrangian subspace, and then we can quantize the theory as usual. And this has been done actually a long time ago in 2008. I refer to this paper if you want to see the detail. Then we move to the evanescent sector. Now, it turns out that the positive Lagrangian subspace, in particular the Lagrangian subspace that defines the vacuum, is also defined by specially boundary condition that we impose on the field. So if we want that our field goes to zero at infinity, I mean at a special infinity for larger value of the radius of the hypercylinder, we really have to select just one kind of evanescent solution, which has this most defined by this Bessel function KL, okay? So we can easily identify in terms of the boundary condition, which is the appropriate Lagrangian subspace that we have to use to construct our vacuum and then the theory, the quantum theory. But it turns out that the inner product in this evanescent sector is not positively definite in this Lagrangian subspace. So we cannot apply the standard quantization techniques. Okay, so this problem actually has a solution, and the solution consists in this new quantization scheme, which is called the α-Kähler quantization scheme, okay? So the main idea is to introduce a new structure, a real structure, alpha, which is a map from the complexified space of solution into itself, that satisfies a certain number of properties. So the most important one, well, they are all important, but in particular, it interchanges the polarization. So this is really analogous to what the complex conjugation does to a positive energy solution. I mean, if you have a positive energy solution and you complexify it, you get a negative energy one, and the alpha do the same. But of course, here we don't have the energy as the main parameter because we are in this strange region, on this strange hypercylinder region. Okay, so once we have this alpha, we can also define a new inner product. Okay, so the form is essentially the same. Here we have the symplectic structure, but instead of take the complex conjugate of the first entry of the symplectic structure, we take the alpha transformed first entry. Okay. So with this new inner product, now we can identify the positive energy Lagrangian subspace of the evanescent sector, and then we can build the quantum theory of the Hilbert space and so on. So this new scheme is called, we call it the α-Kähler quantization, okay? And this has been introduced in this paper of last year, essentially. And in this other one, we give some examples. And now let me show you the first new result of this talk, which is the form of the vacuum in the evanescent sector, so the evanescent vacuum, in the Schrödinger representation. So the states are really functional field configuration of the boundary. And the form is it's a Gaussian, which is determined in terms of this precisely the Bessel function, the KL modes that are exponential decreasing function of the radius. Okay. This corresponds to this choice of alpha. I give here the action of alpha on the coefficient of the expansion. So they have this complicated form, okay? And this state has nice properties. In particular, it can be obtained from the standard vacuum in the propagating sector through an analytic continuation, okay? Also, it emerges as a sort of Wick rotation, limit of the Wick rotated propagator, field propagator that we can define. It's not really a Wick rotated, it's more complicated, and but I don't have time to enter into the detail here. But let me just state the last property, which is the state that really reproduces the standard Minkowski vacuum. So if we look at, for example, the Feynman propagator in Minkowski, so we can also compute the Feynman propagator in this strange region, this hypercylinder region. So we will have a piece of the propagator which comes from the propagating theory and another one from the evanescent. So the sum of these two pieces really reproduce the standard Feynman propagator. Now, for the propagating, the propagating propagator, we essentially have no choice. This is essentially fixed by the theory. But here, for the evanescent one, we have the ambiguity on alpha. So we can have many different alpha that will produce different pieces of the propagator. So there is just this piece here that is here on the top of the slides that reproduce the standard Feynman propagator. So this vacuum is really can be seen as the evanescent component of the standard Minkowski vacuum. Okay.
Sorry, 2-minute warning.
So we have now the quantum theory in the evanescent sector. So we know what is an evanescent particle. And now let's go to the detection. So our starting point here is this paper by Burbano et al., where they introduced this, they modeled the Unruh-DeWitt detector in terms of pairs of Grassmann variables, okay? So now the idea is to put the Unruh-DeWitt detector inside the hypercylinder. Now, our system will be described by a theory, by an action which has three pieces: the free action of the field, the free action of the detector in terms of this Grassmann variable, and the interacting term which couple the field with this detector. So now the idea is to integrate over the degrees of freedom of the detector with appropriate boundary condition and interpret this as an observable for the scalar field, and then compute the observable map that I introduced at the beginning, or let's just mention at the beginning, not introduced. So, okay, this is our detector. Okay, omega is the energy gap, and we can consider two kinds of transition from the ground state to the ground state and from the ground state to the excited state. We will work just in the first order perturbation theory, and we will consider two trajectory of the detector. And let's look at one particle propagating probability. So we take one particle in the propagating sector, we put the detector on the time axis, so r equals 0. And it turns out that the ground transition is simply 0. I mean, the probability of the transition is 0. The probability of the ground excited transition is different from 0. It has a maximum. It depends on quantum number, but it has a maximum when the energy of the particle is equal to the energy gap of the detector. And crucially, this maximum does not depend on the radius of the hypercylinder. Now, if you go to the evanescent sector and we do the same thing, we almost obtain the same expression, apart from this extra factor here that really depends on the radius of the hypercylinder. So changing the radius of the hypercylinder, we change this probability. The smaller the radius of the hypercylinder, the higher the probability. Okay, so this green curve here is really for a small radius, and the red one is for a big radius. Okay, so we still have to explore what are the details of the physics inside this. Now we can do the same thing for the rotating detectors, or detector of the vector in uniform circular motion. And here we indicate with beta the angular velocity, and we have this expression that really depends on the quantum numbers and also on the radius of this motion. It could be 0 depending on the value of this quantum number. Okay, we'll don't have time to enter into the detail of this, so let me just summarize. We can quantize evanescent modes. We have evanescent particle on the hypercylinder, and it seems that this particle can be seen by an Unruh-DeWitt detector. So they're really there, and they contribute to the physics. This is our preliminary result, and then of course the outlook is, well, understanding better this result, confirm this result, look at non-perturbative treatment, for which we have already some preliminary result in collaboration with Christian Schubert, by the way, and also look at more general reason, not just this hypercylinder region. Okay, I don't think I have more time, so thank you very much for your attention.
Thank you, Daniele. So we are a bit over time. Quick question, or okay, but it's very quick, please. Go ahead, Peter.
Thank you very much for nice talk. I'm not familiar with the α-Kähler quantization of the field, so I'd like to know about the Hamiltonian of the system. Usually, Hamiltonian is a Hermitian operator, but in your formulation, Hamiltonian becomes non-Hermitian operators or not?
There are many ways to quantize a field, okay? So there are many ways. The way that we use, actually, we have developed two quantization schemes. One is based on the path integral, okay? And the other one is based on the non-homomorphic quantization, which is, you can see as a kind of deformed geometric quantization, okay? The way to quantize really, I mean, we can define the Hamiltonian. It's not really our fundamental pieces of that we need for the quantum theory Hamiltonian. Actually, we can do it, okay? But what's more important is the action of the field, the path integral, and the possibility of having positive definite Lagrangian subspace. The key ingredient here is positive definite Lagrangian subspace, okay? So this cannot be achieved with the standard Kähler quantization. We have to modify with this quantization, we have to modify the inner product, and with the new inner product obtained in terms of this alpha structure, then we have positive definite Lagrangian subspace, and then we can have the standard quantization.
Oh, thank you very much.
But let's look at the paper because all the details.
Thank you.
Okay, thank you, Daniel, for your talk.